So you remember logarithms from MHF? And previously in other courses and in last semester as well, we talked about exponential functions. So there's a pretty strong relationship between logarithms and exponential functions. And a big part of what we're doing today is just kind of reviewing and remembering what logarithms are and all of the different properties that go along with them and exponential functions and expressions. One trick while you're getting warmed back up with all of this is that if you're ever stuck on something in terms of a logarithm, think about it in terms of exponential, right? Like be able to go back and forth, relate them back and forth. Sometimes we do solve problems by rewriting in a different form. Sometimes we don't, but you can always kind of tap into your understanding by converting either on paper or in your head something that's in logarithmic form to exponential form, that kind of thing. Okay. All right, so let's take a look at this. We got a couple of graphs here. We're going to look at this one first. And who can tell what this is the graph of? Like, what's that function? Or what would be your guess? Can't tell for sure. Anybody have an idea? How would you know? What kind of function is it? Likely. Oh boy. See, this is why we're doing a warm-up day, to make sure that we kind of tap back into this stuff. Well, you got two guesses, because we're doing logarithms, and I said we're also looking at exponential functions. So there's two graphs here. So like, this one's the exponential. So we want to know that that's what that this green curve, I know it's not green on your page, but on mine it's green. You know that that's what an exponential function looks like. I mean, that's like the parent function. We kind of need to know that. How do I know what exponential function it is? Well, I notice a couple of things. I notice it goes through this point. That turns out to usually be an important point. If I have a shift or something, then it might not go through there. But something to the exponent 0 is going to give me 1, right? So that's a typical point. I also notice that it's got an asymptote. That's an important part of the exponential function, that it's got an asymptote in general at that place. And then where can I look to find out anything else about this? Well, I'm going to look to the next point, and I see that it occurs at 10. So what does that tell me? This is going to be 10 to the x, isn't it? So 10 to the 0 gives me 1. 10 to the 1 gives me 10. 10 to the 2 would give me 100. This one's growing very fast. This looks like 10 to the x. There's a couple of important points. Remember the asymptote, all that kind of stuff. So what about the red curve? What do we think it's going to be? So remember the relationship between exponents or exponential functions and logarithmic functions is one is the inverse of the other. So if I take the exponential function and I interchange the x's and y's, I get x equals 10 to the y. And how do I rewrite this as a logarithm? Which is something that I think we're going to practice in a few moments. But the base stays the same. So I get log base 10, but then it's of x equals y. So that's the graph that we're looking at. The base stays the same. The base of the exponential function was 10. So the base of the logarithmic function, if I'm rewriting it, right, remains 10. That's really important. And then the x's and y's flip. So that's the idea there. And again, I see these important points there and there. And it has a horizontal or a vertical asymptote at x equals 0. So it's got similar properties to the exponential functions, but flipped around, right? Reflected over that, the line y equals x. Any questions about that? Kind of remember some of this? So what's going on with this one? What do you notice? Looks the same? Like similar? Would you agree with that? One of them looks exponential, the other one looks logarithmic. Does it look like they're the inverse of each other? One is the inverse of the other. So what do you think the graph of this one is? Nope, not cubic. Oh, like 3 to the x, is that what you meant? Which wouldn't be cubic, but it would be a base of 3. it's close to that. If it was 3 to the x, it would go through exactly that point, I think. If you look carefully, it doesn't. So there's 2. There's 3. It's somewhere between the two. Does anybody want to take an estimate? What would you say it is? Who wants to have a go? Y equals something to the x. Square root of 7. What would that give me as a decimal? Who's got? I'll do it. Square root of 7. That's a nice answer. That's about 2.65. People happy with that? That's pretty close. That is pretty close. It's actually a bit closer to 2.7 approximately. But actually, what it is this really, really important number. So back in elementary school, you learned about a really important number, kind of a magical number. It's the first of its kind, I think, that you see. Although I wonder if when you learned about it, if you were given the appreciation for its magic. Do you know what number I'm talking about? Pi. So you learn about pi, but you probably learn just how to use it to calculate area of a circle or circumference of a circle, something like that. Did your teacher talk about pi? Like they probably said, it's irrational and it goes on forever and ever. They say things like that when you first learn about it. Kind of remember. This is a long time ago now. But who knew that it would show up again in like radians and show up in trigonometry and have all these other applications? And turns out that if you start to research it, it's got all these other applications as well. And pi is a really, really, really special number in mathematics. So that was, I would say, the first one that you learned about. What other important numbers, other than the sort of natural numbers, have you learned about? Can anybody think of another one? It's another like interesting number that sort of opens up a new world to you. Negatives, maybe you could think about negatives, like you learned about negatives, you didn't know about them before, and all of a sudden, but that's a system of numbers, not a number. Irrational numbers? Is that what you mean? Yeah, like square root of 2, that is a special one. Turns out the history of a number like that, square root of 2, is really important. Pythagoras had a cult of mathematicians that followed him, and he denied, this is totally true, you can research this, it's well known. He denied the existence of irrational numbers like the square root of 2, and I guess they didn't really have pi. They probably didn't think about that as a ratio back then. But anyway, this is a long time ago, right? Like 4,000 years ago, something like that. Denied the existence of irrational numbers. Pythagoras loved rational numbers that can be expressed as fractions. And for a long time, in fact, because of Pythagorean theorem, you can find square root of 2, right? 1, 1, root 2, that triangle that we've talked a lot about in trigonometry. And so they knew about it, but Pythagoras thought that kind of blew all of what he believed to be true about mathematics out of the water, so he didn't want people to know that. He thought that math was perfect because numbers could all be written perfectly as ratios of each other, like a half or 3/4, or even 0.333333, a number that goes on forever, is a third, can be written beautifully like that, whereas square root of 2 can't be written as a fraction. Right? We write it as square root of 2, though. It's just a new way of thinking. So irrational numbers, definitely. There's another one. Yeah, right? So that's another one that we don't know a lot about. We haven't used it a lot, but it's definitely something that like opens up a new way of thinking. So this is another one. This is another number. It's kind of more like pi in some ways. And what it actually is we use e. So have you heard that there's a number called e before? You got a button on your calculator. I'm sure that would do that. And if you find the button on your calculator, and mine goes shift, and I hit it, but it automatically gives me an exponent. So it's like e to some exponent. And if I put in a 1 and hit equals, I'll get the value of e to 10 decimals or so. So 2.718281828, and it looks like it's going to repeat, but it doesn't. It's like pi, it doesn't repeat. It's another irrational number, and it's a super important number, which we're going to talk more about, not tomorrow because it's a test, but on Thursday we'll talk a little bit more about what it actually is or why it is or what it does. For now, we're just going to realize that it turns out it's really important, and we're going to start using it a little bit. But it's just a number, okay? It's just another number, like pi, has important applications in calculus and lots of other places. But for us, like we want to start thinking of it as just a number, okay? So if this is y equals e to the x, then I can see that that value there is e, right? About 2.7. So square root of 7 was a pretty good guess. 2.65. It's pretty close to 2.72. And so what is this one down here? It's y equals log base e of x. But e is such an important number in exponentials and logarithms that it's given its whole other notation. And so this is actually the notation that we want. I have this really bad habit of writing that as an H. Whenever I go to write ln, I write it as an H. So whenever I do that, you can laugh at me, but I'll try to fix it. It's ln. It stands for ln, or that's how we say it, ln. So ln of x or ln of anything means log base e. Do you remember in MHF when you talk about how if you don't write a base, if you just write log, so y equals log of x, what does that mean? Means base 10. So that's one of the sort of special ones that we just have an understanding of, that if there's no base, it means base 10. So same thing here, ln means log base e. And again, while you're working through this today and through the rest of this unit, if you're ever getting stuck, just remember, oh, this is like log base e. There's nothing else special about it except that it's log of a particular base. That's what ln is. And we'll find out, like I said, on Thursday, what is so special about that, why this is an important number and the value that it has. Any questions about that? I have seen some software where when you type log without a base, it actually reverts to ln. So it's like generally accepted, I think, at least in North America, that when you write log with no base, it means base 10. But there are instances where people assume it to be base e. So anyway, if you ever are getting weird answers, that maybe is what's happened. If you're typing it into a computer or a calculator. Calculators have a ln button. Mine, where it's e to the exponent, has an ln there. So ln e to the x are inverse. And we've got that. And we're golden, ready to go. Everybody good without any questions? One more thing about mathematical history that's really interesting. So has anybody heard of Euler? Have you heard of this guy called Euler? His name is spelt like this. And if you study mathematics further, you're going to meet this guy. He is people would argue that he is given the most to all of mathematics, like one of the top, or could be argued that he is the greatest mathematician who's ever lived. His name was Leonhard Euler. It looks like it would be Euler, but it's Euler is how you pronounce that. The letter E, so the letter E he didn't discover it, but he used it a lot. And he, I think the reason why it's E is because of him, which is pretty pretentious that he named it after himself when he didn't even discover it. It could also be partially that it's like exponential, right? But he did a lot of work with all different kinds of mathematics. He's famous for this identity called Euler's identity. So it's E to the I times pi minus 1 equals 0. So this is an identity. It's true. It's the very important letter E, or number E, that we've just learned about. You don't need to know this, by the way. This is kind of interesting. To the exponent I times pi, and then you subtract 1 and it equals 0. And does this strike anybody as interesting? What would you say is interesting about it? Like, does anything jump out at you? Mason, what do you think?
How it has 2 special numbers.
It has at least 2 special numbers. How many special numbers would you say that it has? Euler thought those were the 5 most important numbers in all of mathematics. That's what he thought. One is the identity that if you multiply anything by 1, it remains itself. 0 is the identity, obviously, or the number where you multiply anything by 0, it's 0, or you add 0 to anything, you get that number, right? So those are obviously very important numbers, 1 and 0. And then E, we're learning, is important. Pi is obviously important, and I is obviously important. And Euler thought, here's another kind of crazy, kooky fact for you, since we're talking about Pythagoras. Euler thought this was a proof of, like, a god. Euler thought, honestly, he thought that the fact that you can take the 5 most important numbers in all of mathematics and relate them in such a simple, concise way. There's no other numbers. There's a couple of operations, subtraction and exponentiation, but nothing else going on here. And so he thought that must be proof that God exists, which I don't know about that, but that's what he thought. Now, it's kind of trickery in some ways because it also means e to the I times pi equals 1. And if I just pull the 1 over and subtract it, then I get 0. Like, you kind of, but anyway, that's just the way things go. It is a pretty beautiful, it's called Euler's identity. It's a beautiful, beautiful thing. And if you ever meet mathematicians, talk to them about it, they could go on and on about it. And there's a few very interesting videos online that you could look about that. It's a powerful statement. Okay, let's take a look at some of these properties of logarithms, and we're going to just do some examples, remembering the stuff that we learned in the last semester in MHF about logarithms. Log base b of 1 is equal to what? And if you don't know, how could you figure this out? It's 0. How do you know that? Because it's like b to some exponent equals 1, so it's got to be 0. B to the 0 is going to give me 1, right? So log base b of b, as these are really important to know, you got to recognize them. If you don't recognize them, you're going to have a hard time taking derivatives of these things and simplifying expressions. So we got to more and more know these very well. What's log base b of b? It would be 1, because it's like b to some exponent equals b. So b to the 1 is b, of course. And you can always, this is what I'm saying, you can always rewrite. Now, if you're taking a derivative of something, and you have to simplify a logarithmic part of it, you can't rewrite that as an exponent in the question. Okay, this is something that we try to kind of get at in MHF, that we don't want to be always rewriting things. You can off to the side. I can't write log of some base of 1 as b to the question mark equals 1. Like I can't replace that in an expression, you know what I mean? But in my head I can. I hope I'm making sense there. Log base b of x to the n. What is the rule that we can use for an exponent in the argument of a log? What can I do to simplify this? What can I do to the n, Mason? Very nice. N times log base b of x. And we saw proofs of all this, I think, in MHF last semester. Log base b of b to the n will equal, there's a couple different ways you could think about this. But ultimately, what does this one equal? N. I could think about that as n times log base b of b. And log base b of b is 1 from above, so that's just n. Or I can think of that as like b to the n equals b to some exponent. So obviously it's got to be n, right? Okay. Log base b of x plus log base b of y. Who remembers how I can simplify this or rewrite this? And I can obviously go back and forth. Very nice. X times y. Yep. And similarly, when I'm subtracting two logarithms, that's the same as dividing the arguments. Those are really useful to take two things and put them into one, or vice versa. And I don't think that b looks like it's bolded. I don't know why it's not supposed to be. This is a tricky one. It doesn't come up as much. B to the log base b of x is equal to, anybody want to guess? Yeah, it's x. And like, the thing about this, on the test, this always comes up on the test at MHF. You won't see it in calculus, but it may come up throughout the unit, but it won't just be a question like this, I don't think. Some people put the answer as B, but that doesn't really make any sense because, like, you got a couple of guesses here. It's either B or it's X. Probably the B's cancel out and you're left with X, right? Like, otherwise it wouldn't matter what X is or something. I don't know. If you think about it, that's one of the ones where we don't see it very often, but if it ever comes up, you can probably, if you use a little bit of common sense, you can probably guess and just realize, oh, it's going to be X. Or you could rewrite it as a logarithm, like there's all different kinds of things you can do, but it does equal X. Okay, very good. Those are a bunch of the log properties. So if I start applying them to this one, see, it looks different. Ln of 1. Doesn't look the same. What's it going to equal? 0, because it's just log of a particular base, base e. So ln of e, the number, nope. What's it going to be? 1, because this one's like log base e of e. So it's the same as this one here, right? Like same idea, but it's maybe not as obvious when we're looking at it in this notation, but that's what we're trying to come to terms with. All right. You can go ahead and fill in the rest of those. Okay, and they just, I mean, they're the same questions that we saw log base b, but now it's log base e, which is actual number, right? So ln, but it's the same idea. But that's part of what we're doing today is getting used to the notation of ln and realizing that it's a particular base, it's a different button on our calculator, that sort of thing. Any questions so far? We all good? All right. So I want you to go ahead and try this if you can. Right, in exponential form, it's nice to see one of these with numbers that we know. Like those numbers should be familiar, 2 and 32 and 5. Even if you didn't know anything about logarithms, I could say, what's another way you could write those three numbers in some kind of identity that relates them, that makes sense. 2 times 5 equals 32. That doesn't make any sense, right? That's not right. 32 divided by 5 or something like that doesn't work. Like, what is the way that you could write those three numbers together? And I think we'll see that it's 2 to the 5 is 32. So this is what I mean by, like, hopefully we know that 2 to the 5 is 32, and this is a nice way of making the connection in our heads. Or if you want to use something simpler, then 2 to the 8 is 3. Like, you use numbers that you know. Don't use 2 to the log base 2 of the 4 is 2. Don't use that one. That's a terrible example. Log base 2 of 8 is 3. Like, use the ones that you know, but it helps us flip back and forth. When you first started working with logarithms last semester, it's strange at first, right? Like you're slow at it because it's a new notation and it's a different way of thinking about things. At least I find that it's quite a different way of thinking about things. Even if you're like a teacher or a mathematician, if you haven't used it in a long time, it takes some time to kind of warm back up and get back into the swing. But you might remember by the end of the unit, you were kind of getting into it, right? And you're like, okay, now I'm seeing logs for what they are. So you might remember that. Okay, that one's done. And just to point out again, remember, the base stays the same. Log base 2. And then what's the base of the exponent? It's the base of the exponent is 2. 2 to the 5, the base is 2. So that's my little trick. The base stays the same that I always like to kind of recite in my head to make sure that I've got it. So Turns out the ln of 44 is about 3.784. So how would I rewrite this one? Yeah. It is approximately 44. Nice. Could do this on your calculator. In fact, why don't you try just so you find that button and get used to it. So if I go ln of 44 and hit equals, I get 3.784. And if I hit e to the 3.784, I get, whoops, shift would probably help. 3.784, I get just under 44, 43.99. All right, rewrite that one in logarithmic form. Base stays the same. If you wanted to do it in 2 steps, you could. In your head, at least, you could go, okay, so that's log base e. And then I flip the other 2 parts, so 148.41, and that's going to give me about 5. But log base e is ln, so that's how we want to start writing it. And again, you could try punching both of those into your calculator and make sure they work. Make sure they're actually right, and I didn't just make them up. Yeah, it looks right to me. What about b? What are we going to do for b? Any ideas? It's not. I don't think this is one that's going to come up very often, but it's good to get us recognizing what these things are. Possibly could, yeah. What else could we do? But there's a step before that that might even simplify things. Can't I just rewrite that whole thing as an exponent? Like, that's an exponent, right? We recognize that. We want to see that, oh, it looks like the 3rd root of e squared, but it's actually e to the 2/3. And that's approximately 1.948. So then that means the ln of 1.948 is approximately 2/3, which I think what you said is 3 times the ln of 1.948 equals 2. I think that's kind of what you were saying, right? And so there you go. There's another way of seeing that. But I think what Mason was probably doing was like applying one of those properties from above, which is very good. Any others here? Any questions? Stop me. We're going to keep going. Evaluates 2 decimal places. How are we going to do this? Just on a calculator. Go ahead and give it a try. Who's got the first one? Jason?
4.9558.
Okay, nice. So to 2 decimal places would be 4 point. Thank you. Very good. Ooh, this next one's tricky. I don't know if this calculator on here has. It doesn't have a ln. If there's any way of bringing it up. No, that's not going to work. Nope. Nope, nope, nope. Oh, programmer. Nope, nope. Darn. This next one, e to the 4, is 54.59815. So be careful. This is one that like grade 9s have a real hard time with. Yeah, 54.60. Make sure you get that 0 in there. 2 decimal places. We keep the 0 right. Not something we see very often because we like exact answers. A lot of what we're going to do, we'll be working with exact answers as well, but sometimes we'll have to round. And these next two, I don't need my calculator. What's the first one? Good. And what's the second one? D. (61). Log base e of e to the 61, right? So remember, ln means log base e. Okay. Continuing on. Again, today's just about getting warmed up and getting used to this kind of thing. So don't overthink how you know which type of question is which. In MHF, sometimes we solve equations by rewriting in exponential form. Sometimes we solve equations, but we don't rewrite. Or we evaluate expressions as is or by rewriting. And there's all these different things. But that's all just made up math class stuff to practice our skills. So there's no secret about how you would solve which type or anything like that. In this case, we're going to rewrite. So how could I rewrite ln of x equals 10? Very nice. And then I can just evaluate it on my calculator. So e to the 10 is probably going to give me something big. Good. And we're supposed to do 4 decimal places now, so I'll keep going. That's okay. 4, 6, 5, 8. It looks like. E to the 3x equals 50. So again, what you do want to notice is this would be hard to solve with the x where it is, and rewriting in logarithmic form is going to bring the x out to a place where I can isolate it. That's, I guess, what you want to be observing here. So the base stays the same. So this is 3x equals log base e, which is ln of 50. And I'm going to isolate this further and put the whole thing into my calculator. So ln of 50 all divided by 3. And I got 1.3040. And same thing, if I have a statement like this, ln of 2x, well, this is similar to the first one that we did in some ways, except it's got a little bit more to it. But the x in the argument of the ln or of a log, that would be tricky to solve for. So what can I do? I can rewrite this in exponential form, and that will pull the x out. So I'm going to end up with 2x equals e to the 1.1. I got 1.5021. Any questions about that? Got a couple more types here that we're going to take a look at. We're going to look at 4 different questions here, but there are similarities between all of them. And after we finished all four, you could go back and you could like look at all four sort of at the same time, sort of glance at all of them and see how different they are, but how we're ultimately trying to do the same type of thing. And this reminds me of solving trig equations as well. What about this first one? This first one's pretty straightforward. It's already kind of halfway done, you might think. What am I going to do? If I multiply two things and they give me 0, then what can I deduce from that? John? Yeah, so this is like already kind of done for us, and I get ln of x plus 2 equals 0, or ln of x minus 3 equals 0. So that means ln of x is negative 2, ln of x is 3, and be careful with exponential function. It's never negative. Think about the graph. In fact, I'm just going to scroll up. Why don't you look for a minute? There's a couple of ways, and again, this is something that if I look here, you've got this on your handout. We probably could have talked about it before. That would have been a good idea, but log base b. So b is greater than 0 and x is greater than 0. The base of a log can't be negative, can't be 0, and the argument of a log can't be negative, can't be 0, but the y value can be 0 or can be negative. And I could look at the graph and think about that too. Look at the graph for log or for ln. It goes in positive y's and negative y's. There are x values that don't work. Right? So where's the x value? That's the argument there. There are x values that this graph will never touch, never be there. And that's sort of the opposite, or the inverse, we would say, from exponential function, right? So when I'm thinking about the possibilities down here, this will work. This means x equals e to the negative 2, so x equals 1 over e squared. There's nothing wrong with that. And this is x equals e cubed. And if we're doing exact answers, which is what we will leave it as, we're done. That's the answers that we want. That's fully simplified. Don't stop there. Don't forget to figure out what x actually is by writing it as x equals. That's when you're done solving an equation, when you have x equals something. And in this case, we can write nice, simple answers, so we'll leave those the way they are. We don't need to evaluate them. Okay. Next one. Any ideas for this one? You can factor it. What makes you think that you can factor it? Like, how do you recognize that? Yeah, so I could off to the side in my head, or you could do it in place, or you could do it in your margin. Replace ln of x with something. So a squared minus 3a minus 10 equals 0, where a is the ln of x, and it's just a simple trinomial. Very good. So it ends up being, what are my two numbers? It looks like minus 5 and 2. And it would be like a minus 5, a plus 2. But instead of a, I write ln of x and ln of x. Okay, you want to finish those? Let's get that. Pretty much the same as the last one. E to the 5 and 1 over e squared again. Worked out the same. Okay, we got a couple more here. I want you to think about C for a minute and how is it different, but then I want you to think about how it's the same idea as what we did in the last two questions. Like ultimately when you're solving an equation, that's what you're working towards. But this one's set up a little bit differently, so think about that. See if you can recognize what's going on. We certainly, you may never have seen something quite like this, but we certainly have the skills to solve it. Patty, what do you think? I think we can. Doesn't it look like you can do that? So what would that look like? Can you do that for me? Oh yeah, right. You don't have this on a handout. So x cubed times e to the x minus 8 times e to the x equals 0. So if it's a common factor, I'm going to be able to factor out e to the x out of both of those. And what am I left with? X cubed minus 8. And all of that is equal to 0. So again, what's the common thread here? What's the common denominator, the common principle practice that we're trying to do is we're trying to get it to be a product of two things or multiple things, however many things it works out to. Usually it's 2. And then any of those two things are equal to 0, and they're solvable. That's obviously key. And this reminds me of solving trig equations. Remember when I said that? Where you're always somehow, whether it's using an identity or by common factoring or whatever it is, you end up with, you might have sines and cosines and all kinds of stuff in the same question. Ultimately, you got to split them up so you have things that you can actually solve. So e to the x equals 0, or e cubed minus 8 equals 0. And there's a couple of ways that you could solve this. This one's x cubed equals 8. So if I take the cube root of both sides, I get x equals 2. Not plus or minus. This is for a cube root. We don't do that, so it's just 2. And what about this one? E to the x equals 0. How am I going to solve this? There's different ways that you can think about this. I might rewrite it. Log base e, right, of 0 equals x. And take the ln of 0 on my calculator. What's that? Try it. Math error, doesn't work. Remember the graph. E to the x equals 0. When does the graph of e to the x equal 0? When does it have an x-intercept? That's another way of thinking about it. See how there's all different ways. Once you get functions, you can use that graph to think about the nature of the roots, of the solution, all that good stuff. And we know from the graph, there's an asymptote there. It never will reach that. And we also know that ln of 0, that doesn't make sense. I can't input 0 into the graph of y equals ln of x. That won't work. So this is no solution. Okay, one more. What does this one look like? Anything? Again, a lot of solving new problems has to do with like a gut check. Like you may not know how to solve this, and this is part of the problem. Is a lot of people are hesitant to solve problems that they haven't seen before. They're hesitant to try, but that's a big part of the level of mathematics that we're at. Is like we got to start being better problem solvers, getting used to new problems and new areas. So I would say, I mean, even if I'm not sure if this is going to work, what does it kind of at least look like? Yeah, look like there's three terms. It's a trinomial kind of thing. It kind of looks like maybe it's something like that. But if you weren't quite sure, what if I rewrote it like this? E to the x all squared. Because like a to the b, all of that to the c is a to the bc, right? You can multiply the exponents. So I could use that and work backwards. E to the x all squared plus e to the x minus 6 equals 0. And then again, this is kind of like a squared plus a minus 6 equals 0. So I can factor that. It's just a trinomial factor, don't you think? E to the x plus 3 e to the x minus 2. It's an easy factor in the end. Equals 0. So e to the x is negative 3 and e to the x is 2. If e to the x is negative 3, what does that tell us? No solution. That's like ln of negative 3 is x, and there's no solution there. And this one's x equals ln 2. Any questions? That's it. Last example.